So let's take a look at another example where we're going to try to optimize a particular quantity. Let's see what we have here. Looks like I have a small typo to start. A factory needs to make a cylindrical can which can hold 1 liter, which is the same as 1,000 cubic centimeters of oil. Okay, so a factory is producing cans of oil. Now the key here is that this factory wants to find the dimensions of the can, that is the radius and the height, that will minimize the amount of metal that's needed to manufacture the can. So that way they can produce these cans for as cheaply as possible. Now you can start to kind of understand the scenario here a little bit by drawing out a little bit of a picture. So imagining that I have a cylindrical can that looks like this, I can see that again, this can is going to have a radius for that top and bottom circle, and of course it's also going to have a height over here on the side. Now, I can make a can that holds 1,000 cubic centimeters of oil, and you could imagine I could make like really long, skinny cans, right? Like I could do a can that looks something like this. I can make cans that are unbelievably wide and very, very short. But I might want to try to figure out like exactly where in between these kind of two extremes do I want to be so I can get a can that meets the criteria here, but also kind of uses the least material to construct it. All right, so let's see what we would have here. The first thing that we should note is that we want to minimize the cost of the can, and we want to minimize that by reducing the amount of material that we're going to need. Notice here, though, that the material used to make the can is going to correspond to the edge of the can, the top of the can, as well as what would be on the bottom of the can. So what we can say is that what we're really interested in minimizing here is the surface area of the can. Now, the surface area of the can here will represent by just the value S. So we'll say S for surface area. And it's actually really easy to find the surface area of the can. Notice here that we have a circle on top, and that area formula would be pi r squared. We have the same size circle on bottom, and so we're going to have another pi r squared contributing to the total surface area. The harder part of the surface area is understanding this section here around the middle. But to see this a little bit more clearly, imagine we had already removed the top and the bottom, and that then I made a cut right here along this edge, and I kind of unwrapped this cylinder shape, and if I unwrapped it, I could actually see that what I would end up with is a flat rectangle, right? And I could imagine like the cut would have been existing right here. So if I kind of rejoin these edges back together, I'm going to go ahead and create the cylinder shape. So this actually makes it a lot easier to understand how I find the surface area for this outside cylindrical piece. What I can actually use is the height multiplied by the length of this rectangle. The weird part, though, is that I can see that when I wrap this rectangle back up into the cylinder, this top length that would exist right here is actually going to fall in the shape of this circle. So the side length here is actually 2 pi r. That is the circumference of this circle, the length of that outer edge. And then, of course, I have the value of h here on the side. So I would actually have 2 pi r h as the additional piece of surface area that I need. Notice then what I really end up with is 2 pi r squareds, two circles, one for top and bottom, and then the kind of wrapped up rectangle that exists on the side. What you'll notice is that if we look back in the formula box that we had up here, we'll see that this surface area for a cylinder actually looked exactly like this. But we can almost kind of think this through as opposed to just memorizing the specific formula. So if this is what we actually have here, now we can go ahead and start to think about if I wanted to take the derivative of this, again, it would be way easier if I had this instead as a function with one variable. Right now I have two variables. So we have here too many variables on, the right-hand side. We want to get rid of one of those by using something else that we know here. So there's only one other piece of information that we know in this problem. Can you spot what it is? Well, we know how much the can is supposed to hold. We know that the volume of the can should actually end up being 1,000 cubic centimeters. Well, the volume of this can, remember, since this is the volume of a cylinder, should be found by doing pi r squared h. So that means we know that this is supposed to be equal to 1,000 cubic centimeters. Notice then that I could state that the value of h is really this 1,000 over pi r squared. And with this, I could now replace the value of h and make this a formula with only one variable. So notice that if I do that here, I'm going to have 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Now I'm going to simplify this up a little bit, and I can see a couple things are going to cancel out. I have an r here on the top and 2 on the bottom, so 1 gets removed. I can also simplify out these pi's. So I end up with the formula 2 pi r squared plus, I'll make this 2,000, 2's multiplying to the top, over r. Or I could also rewrite this then, since that's divided by r, as 2,000 times r to the negative first power. Now again, notice what I have here is a formula that's technically able to kind of be expressed as s of r, right? There's an r. If I know the value of r, I can compute the value of s. So this is very similar to like when I had functions with f of x equals a bunch of stuff with x. I can now take the derivative and find a value of r that is going to maximize or minimize that surface area of s. So let's go ahead and calculate the derivative. So we calculate that s prime of r is going to be equal to, let's see, it's going to be 4 pi r to the first power plus, oh wait, this negative 1's going to come down, so I'm just going to change this plus right away to a minus. It's going to be minus 2,000 r to the negative 2. Now I need to find when this is going to be equal to 0 and when it might be undefined. So to do that more simply, I'm going to go ahead and rewrite this with positive exponents, and then notice here that I could actually combine this all into one fraction. I could easily do this by getting a common denominator of an r squared, and that would give me a 4 pi r cubed minus a 2,000. Notice I get r cubed because I have to multiply this part here by r squared over r squared. So now that I have this, I can easily state that s prime of r is equal to 0 when the top of my fraction is going to be equal to 0. And of course, I can easily see then that that makes r forces r to be equal to 2,000. When I add that over, I'd have to divide by 4 pi, and then I would have to cube root this value. Now I can simplify this inside of the radical just a little bit. 2,000 divided by 4 is just going to be 500. So I have 500 over pi and a cube root. So that's my exact value. Now if you were to go ahead and type this into a calculator to get a decimal approximation, you'd see this is about 5.42 centimeters. So this is the optimal value, it seems, for my radius. Although I should be careful. This is the optimal value to potentially maximize or minimize. Remember, critical values only tell you potential spots where you might maximize or minimize. I have to look, though, at to see if this actually corresponds to a maximum or a minimum surface area. Now, before I do that, I'll also note that s prime of r is undefined when r squared is going to turn into 0, which of course implies that r is equal to 0. Now, I can see here that automatically, since I'm going to be constructing a can here, I can probably realize that r being equal to 0 is not really going to be a valid option. So I'll put here that we are constructing a can, right? So if I'm constructing a can, I can't have my radius be 0, then I would have no can. So even though this is a critical value, it's not a realistic critical value. I know that's not going to correspond to a minimum surface area, or at least it will create a very small surface area of 0, I'll have no can. But then I can't meet the criteria for making sure that the can holds a liter of oil. So let's just go ahead then and check this critical value right here. So I'm going to go ahead, I'll draw out my number line. I'm going to put my cube root of 500 over pi right here. Again, I'll note that that's roughly the value 5.42. So maybe I can say I'm going to plug in something like a billion over here on this side. Well, notice if I was to plug in the value of a billion, I could see that the top of my derivative is going to be 4 times pi times a billion cubed. That's going to be huge. Minus 2,000, that's definitely going to produce a positive value. And the denominator produces positive, so the whole thing is definitely positive. Notice though, something less than 5.42 would be something like 1. If I do 4 times pi times 1 cubed minus 2,000, that's going to give me a negative value on top. But the bottom, of course, is positive. So a negative over a positive produces a negative. And so what I end up with here is I can see that at this value of r, I'm going to end up with a minimum value. And since, of course, this is the only value that I've found, according to that theorem we stated in the first video, I know this is an absolute minimum. So now I can easily reach my conclusion. So the minimum surface area is obtained when r is equal to the cube root of 500 over pi. Again, we know this is roughly the same as 4.52 centimeters. And of course, I need to make sure that I've actually answered the question. Notice here, though, I want to find the, find the dimensions of the can. So I want the radius and I want the height here. And so in that sense, I need to make sure that I go back and also compute what h should be. But much like we saw in the last example, I already have a little formula that tells me what h is. I just have to do 1,000 over pi and then the value of r being squared. So I'm going to do 1,000 over the value of pi, and then I'll take my value of r and I'm going to end up squaring it. So this is actually going to get really, really messy, but if you were to type this into a calculator and actually approximate its value to 2 decimal places, you would see that I get 10.84 centimeters. So I have found the dimensions that are going to minimize the amount of surface area for the can while still allowing it to hold the required amount of liquid, and I have done what the question asked, which is round my answers to the nearest hundredth.